Let's jump right into this explainer with a number that honestly kind of blows my mind: 50%. Next time you're looking out over a city skyline, keep in mind that conventional air conditioning systems can account for more than half of a building's peak electricity demand. That is a massive amount of energy dedicated just to keeping our indoor spaces cool, and it highlights a colossal infrastructure bottleneck we really need to talk about.
So today, we're exploring district cooling and how it's revolutionizing urban climate control. We're talking about a complete paradigm shift, moving away from those loud, isolated AC units humming away on every single window and rooftop, and shifting toward elegant, city-scale cooling networks.
Here's our roadmap for today. We'll start with the core air conditioning problem, enter the world of district cooling, see exactly how the system works, look at greener grids and storage, and wrap up with the perfect fits for DCS.
Let's kick things off with Section 1, the air conditioning problem.
You see, traditional AC hits our power grids the hardest right when electricity tariffs are at their absolute highest. Picture a scorching summer afternoon. Every single building's AC kicks into overdrive at the exact same time. It's literally the worst-case scenario for the grid, heavily straining building budgets and municipal power supplies alike.
And then there are the hidden costs of conventional AC. When every building operates as its own little island, you need individual chillers and dedicated cooling towers. That demands heavy upfront capital costs, and it completely eats up valuable service and rooftop space. Instead of a beautiful rooftop terrace, you're stuck wasting premium real estate on redundant mechanical clutter.
Which brings us to our second section. Enter district cooling.
District cooling is essentially a centralized network that uses underground, insulated pipelines to supply chilled water from one central plant to multiple buildings. Think of it like a municipal water supply. You wouldn't dig your own well in the middle of a dense city, right? So why are we generating our own localized cooling? By consolidating these needs, the system unlocks massive economies of scale.
When you compare conventional AC directly against district cooling, it is a total game changer. Connecting to this network completely eliminates a building's need for individual chillers and cooling towers. Boom! You instantly get your rooftop space back, you slash your capital costs, and you shrink your building's overall energy footprint.
All right, Section 3. How the system works.
The whole thing functions in 4 beautifully straightforward steps. First, a central plant produces the chilled water. Second, closed-loop, highly insulated underground pipes distribute it across the network. Third, the connected buildings draw on that water to cool their spaces. And fourth, the warmed water returns to the central plant to be rechilled. It's just a highly efficient, closed-loop humming silently right beneath our feet.
Moving right along to Section 4, greener grids and storage.
Operating at this massive scale unlocks some incredible decarbonization benefits. Because you're managing energy at a central hub, the plant can easily integrate renewable energy sources, and it can even recover waste or surplus energy from other industrial processes that would otherwise just be thrown away. This dramatically improves overall grid flexibility, making the whole setup incredibly attractive for large-scale, national energy planning.
And this brings us to thermal energy storage, or TES, which is absolutely crucial here. TES allows the system to shift cooling loads and manage peak electrical demand. Think of it like a giant rechargeable battery for cooling. The central plant chills a massive reservoir of water overnight when power is cheap, and then deploys that thermal energy during the hottest parts of the day, taking serious pressure off the grid.
Finally, Section 5. Perfect fits for DCS. Now, where does this technology actually work best? Well, district cooling absolutely thrives in areas that have high cooling demand density and high load diversity. Basically, you want a lot of buildings packed closely together, but you definitely don't want them all demanding their maximum cooling at the exact same time. That's exactly what we mean by load diversity, or non-coincident peak loads. An office building naturally peaks at noon, right? But a residential complex peaks in the evening when everyone gets home. By linking commercial zones, residential areas, healthcare facilities, and educational institutions, they can efficiently share the exact same central cooling capacity around the clock.
If we look at places experiencing explosive infrastructure growth, like the Indian context, for example, there are some perfect habitats for this. We're talking mixed-use or major redevelopment projects, sprawling aero-cities, and industrial clusters like pharma cities. It's also tailor-made for IT parks, massive data centers, smart city initiatives, and large academic campuses.
So, I'll leave you with this. Is it time to fundamentally rethink how we cool our cities?
When you consider all that wasted rooftop space, the massive capital spent on redundant equipment, and the sheer strain on our power grids, maybe we're finally ready to move our cooling underground. It might just be the invisible infrastructure our future cities desperately need.